Hello everyone, welcome to my class. In today's class I'm going to cover logarithmic functions. So let's start the class right away. Quick overview. So far we studied the inverse functions and the exponential functions in our earlier sections. So now we will use the concept of those functions to develop an understanding of the logarithmic functions. Note, the exponential functions and the logarithmic functions are inverse of each other. That is, the inverse of exponential functions y equals to b raised to the power x is x equals to b raised to the power y, which is then equivalent to the functions y equals to log x with the base b, and we call these functions the logarithmic functions. So let's start with the definitions. Logarithmic functions. The functions y equals to log x to the base b is called logarithmic functions and is defined by using the equivalence relations y equals to log x with base b if and only if x equals to b raised to the power y. So this if and only if means equivalently. So y equals to log x to the base b is equivalent to x equals to b raised to the power y. So this side is a log function, this side is an corresponding exponential functions. So the domain of log function is 0 to infinite excluding 0, and the range is whole real lines. Great. So let's move on. Great. Now let's move on. So conversion chart. So this side, the first column is a log forms, and the second column is an exponential forms. So first row, that's the definitions here. Y equals to log x to the base b is equivalent to x equals to b raised to the power y. So here, let's focus the base b for the log function and base b for the exponential function remains the same, and here this is the argument for the log function. So this x is here and this y, we need to raise the y to the base b toward the exponential side. So here I use a different color so that you know what's going on here. So let's do some other examples. Let's say we have y is 2 and x is 25, b is 5. So 2 equals to log 25 with base 5 is equivalent in exponential form is 25 equals to 5 raised to the power 2. I think this is on your, I zoom in here in our second diagram here. So 5 square equals to 25. Then log 25 base 5 equals to the 2. So the here base remains the same. I hope this makes sense to you all. Now similarly, let me read on this third row here. Negative 2 equals to log 0.04 with the base 5 is same as saying 0.04 equals to 5 raised to the power negative 2. Similarly, log of 1 over 8 with the base 4 equals to negative 3/2 is same as saying 1/8 equals to 4 raised to the power negative 3/2, and log 0.01 with base 10 equals to negative 2. This is same as saying 10 to the power negative 2 equals to 0.01. Great. I hope this conversion chart makes sense to you all. Now let's move on. Quick side notes. Log x, here is no base here. This means this is a common logarithm with base 10. So log x equals to log x with base 10. ln x is called the natural logarithm with base e. So ln x equals to log x with base e. So in our calculator we have log x and ln x. So log x means log x with base 10 and ln x means log x with base e. And we know e is a number 2.7182 dot 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 we introduced in our previous class. Awesome. Side note 3, log of b with the same base b turns out to be 1, and log of 1 with any base b turns out to be 0, and log of bx with the base b turns out to be x. Some applications of log x are in pH scale, means measuring acidity, and the Richter scale, measuring earthquake, and ln x is in radioactive decay or half-life. Change of base formula. Suppose given log function has base b, and if you want to change this base b to our desired base c, then the formula is log a with base b equals to log a with our desired base c over log b with our desired base c. If I pick c equals to 10, this is simply log a over log b, or if we pick c equals to e, then this fraction is simply ln a over ln b. I hope this makes sense to you all. Great. So now let's do example 1. Determine the value of log 125 with base 5 without using a calculator. You begin the solutions. So let x equals to log 125 with base 5. Then use the definition of log functions. Then this is same as saying in exponential form 5 raised to the power x equals to 125. And now to solve this exponential equations, let's try to use a uniqueness property. To apply the uniqueness property, we are looking the same base towards the right hand side also, so we can rewrite 125 equals to 5 raised to the power 3. Then we can equate the exponent, so x equals to 3. Great. Or you can use the side note 4 with this idea. Then it says log bx with the base b turns out to be x. So now here let's rewrite 125 equals to 5 raised to the power 3. Then our base is 5, that means this equals to simply 3. Awesome. I hope it makes sense to you all. Now let's move on. Next, let's talk about graphing the logarithmic functions. Example 2, let's graph y equals to log x with the base 2. So the idea, first graph y equals to 2 to the x. So this is an equivalent exponential form of this given log functions, and we know log functions and exponential functions are inverse, so that means we can reflect the graph of these exponential functions towards the diagonal line y equals to x, and that reflected graph is the graph of these log functions. Awesome. So let's make a table here. Here are the x values, so we can pick some negative numbers as well as some positive numbers and evaluate the 2 to the x. So when x is negative 2, then 2 to the x turns out to be 1/4. So the point on exponential graph is negative 2, 0.25. And since the logarithmic function is the reflections of exponential functions or the graph across the y equals to x, so I am switching x and y coordinate here. So the point on the logarithmic functions graph is 0.25, -2. I'm just switching. I hope it makes sense to you all here. X coordinate becomes y coordinate and y coordinate becomes x coordinate. Now similarly, when x is, let's say, 0, then the point on the exponential graph is 0, 1, and point on the log graph is 1, 0. Similarly, let's say when x is 3, the point on the exponential graph is 3, 8, and the point on the logarithmic functions graph is, just switch it here, 8, 3. And now plot those points on the graph. So here I graph here, let me scroll down. Yep. So this is the diagonal line, and this is the graph of 2 to the power x. We graphed these functions also in our previous sections. and now we are reflecting this graph of these exponential functions across the line y equals to x. So then this is the graph of logarithmic functions with base 2. Great. I hope this makes sense to you all. And one more quick note. So if you graph those points from this fourth column and join, this gives you these log functions. Awesome. So now, quick alert. The inverse of this exponential functions y equals to 2 to the x is not y equals to 2 to the power negative x. So that's a common mistake most of the times we make. Instead, this is the y equals to log x to the base 2. So the inverse functions of exponential is logarithmic functions, and inverse function of logarithmic function is exponential functions. Awesome. Now let's move on. So now here's a quick summary. The comparison between exponential functions and logarithmic functions. So the first column for exponential functions, second column for logarithmic functions. So the domain of exponential function is all real numbers. That means the range of log function is all real numbers. We know they are the inverse to each other. Similarly, range of exponential function is 0 to infinite, excluding 0. That means the domain of log function is 0 to infinite. Let me go back to the diagram here. So now here's exponential functions is this one. So its domain is everything. Range is 0 to infinite. Log function is this one. So the domain is 0 to infinite and range is everything. For the exponential function we have HA, horizontal asymptote, which is x-axis, and for logarithmic functions we have VA, vertical asymptote, which is y-axis. Both of these functions are increasing. Exponential increases faster than logarithmic functions. Great. So this information is here. Both are 1-to-1. They pass the horizontal line test. Exponential function has HA, x-axis. Logarithmic function has VA, y-axis. The intersection point, let's see here. The exponential function intersect the y-axis at 0, 1, and now reflect that point 0, 1 along the diagonal line y equals to x becomes 1, 0. So this is the point of reference for logarithmic graph, which is here. Awesome. So the x-intercept for log function is 1, 0. Both functions are continuous and both increases. The log function increases when b is greater than 1. Awesome. I hope this comparison makes sense to you all. So now let's move on. Next, graphing logarithmic function using transformations. The idea is similar to graphing the exponential functions. So plot the reference point. Here the reference point is 1, 0 for logarithmic graph, and the vertical asymptote is y-axis, that is x equals to 0. And so the transformations of them with respect to the transformations we applied. So now let's do example 3. Graph the functions, the logarithmic functions here. Log of x minus 2 with base 2 and then plus 3 using transformations. So again, now let's begin the solution. So start with the parent functions. Here the parent function is log x to the base 2, and in the next transformation subtract 2 on the x coordinate. That means shift right and then add 3 on the y values. That means shift upwards 3 unit. So let me scroll down here. So here start with the parent functions here, y equals to log x with the base 2, then shift to the right because we are subtracting 2 from the x, and then we are adding 3 on the y value. That means we are shifting 3 units up. So the point here 1, 0 is the reference point on the logarithmic graph. Here we shifted 2 units to the right. That means we are moving 1 to 1 plus 2, which is 3, keeping y as it is. And in our final transformations we are shifting 3 units up. That means we are only adding 3 on the y coordinate, keeping the x coordinate as it is. So here is 3 as it is. 0 plus 3 turns out to be 3. So the new point is 3, 3. Similarly, the vertical asymptote. So vertical asymptote for the parent function's graph is x equals to 0, which is y-axis. And in our first transformations, we shift the graph 2 units to the right. So that means our VA also shifted from x equals to 0 to x equals to 2. And then in our final transformations, we shifted the graph 3 units up. That means our vertical asymptote remains as it is. I hope this makes sense to you all. Now let's use those two informations to sketch the graph of this given logarithmic functions. So here, that's better. So here point 3, 3 is from here. It's 1, 2, 3, and then go 3 units up. 1, 2, 3. That's the point. And vertical asymptote is x equals to 2. 1, 2. This is the vertical asymptote. So then graph of this transformed log function is this one. By the way, I also have this parent functions here, y equals to log s to the base 2 here. So we started from here and we use transformations idea and we found the graph of this given logarithmic functions. Great. So I hope this makes sense to you all. So now quick aside, by the graph, the domain of this given logarithmic function is 2 to infinite. Here the 2 is excluding, and the quick proof here. So to define these log functions, we want this argument x minus 2 is strictly positive. So then this gives me the domain is 2 to infinite. Awesome. So next, let's talk about finding domains of logarithmic functions. So the idea is we need to use a sign chart to determine the domain of the logarithmic functions. Let's do example 4. Determine the domain of the logarithmic functions. Here the logarithmic function is log of x plus 3 over x minus 5 with base 9 plus 2. Solutions. To define these logarithmic functions, we need this argument, this fractions, x plus 3 or x minus 5 is strictly positive. So that's where we are starting here. Then we need to find the zeros and VAs of this fractions functions. So the zeros are the zeros of numerator and zeros of denominators are the vertical asymptotes. So here x equals to minus 3, zeros of multiplicity 1, and VAs is at x equals to 5 with multiplicity 1. So we know in multiplicity is odd number, then the graph crosses the x-axis. Great. So now let's look the sign chart. Draw the number line or the x-axis and plot those zeros and VAs here. X equals to minus 3, x equals to 5. Since multiplicity is odd, so both sign changes here. So now let's pick a point in between these two numbers. So here let's pick the 0. When x is 0, then put x equals 0 on y equals to x plus 3 over x minus 5. x0 plus 3, x0 minus 5, so y equals to minus 3 over 5. We don't care the value, we only care the sign. So this is negative. That means the sign of this y is minus here on these subintervals. Since the multiplicity of zeros and VAs is 1, so the sign of this y changes. So this side is plus, this side is plus. I hope this sign chart makes sense to you all. And then what we are looking for, we are looking for the positive. That means our domain is this intervals union this intervals. Hence, the domain of given logarithmic function is x belongs to negative infinity to negative 3, excluding negative 3, union 5 to positive infinite, excluding 5. This is the interval notations. Great. I hope it makes sense to you all. Now let's move on. Remark: one very practical application of the logarithmic functions involves earthquake intensity. So the formula is the magnitude of intensity equals to log of I over I0. Here I is measured intensity and I0 is the reference intensity. Great. So now here's again the log has a base 10 here. We don't need to write the base 10. Example 5. How many times more intense than the reference intensity I0 is an earthquake with a magnitude of 6.7 Richter scale? Solutions. Here is a formula. So here's mi is 6.7 equals to log of I over I0. So log has base 10, so that means we can rewrite this logarithmic functions in terms of exponential functions. So then 10 to the power 6.7 equals to I over I0. Here's a this I0 is missing here. Then we cross multiply. So then I equals to, oh no, here, no, that's good here, this is good. So then next, so here's I equals to 10 to the power 6.7 times I0. So then using calculator, 10 to the power 6.7 turns out to be this big number times I0. We do know the I0 is simply the reference intensity. So that is an earthquake of magnitude 6.7 is over 5 million times more intense than the given intensity. Awesome. I hope this makes sense to you all. Now let's move on. One final observations here. Logarithms grow slower than the exponential functions. So this is the graph of the exponential functions, and these are the graph of logarithmic functions. If you increase the base in the exponential functions, this increases or this grow faster. If you increase the base for the logarithmic function, this grows slower than the logarithmic function with the smaller base. So here the base is 2, here is the base is e. Base e means 2.7182, and then here the base is 10. So I hope this comparison makes sense to you all. So we finish the logarithmic functions in today's class. Thank you.